Hello, everyone watching this on YouTube. Today, the goal is to basically go through proof of time a little bit on high level and also look into the implementation to understand what it is, how it works, why it works the way it works. And then, if you decide to look into the implementation, you would actually understand what to look for and why things are the way they are. It might be a little bit counterintuitive at first. The spec is not like super tiny. So I hope this will serve as a background kind of information for people to understand it. And hopefully there will be some questions regarding proof of time, and I'll try to answer them. If I can't, maybe Daria will help. So let me share the screen. Have a window dedicated for this. Okay. So you should be able to see this. This is our spec on Notion. And let me start a little bit with the background. What is proof of time? Why we have it? Why we want to have it? Proof of time is basically a process we introduce into the protocol that tries to prove that a certain amount of time, like physical time in real world, has passed between two slots. And there are several ways to actually achieve that. There are VDFs, which are supposed to be delay functions that can be verified that they have taken a certain amount of time to get from slot to slot, or like from one point in time to another. In Solana, I believe they're using hashing functions, just iteratively hash. In our case, we are using AES after extensive studies with supranational and otherwise. We have identified that there is a fairly efficient implementation of AES in modern processors, x86 64 processors specifically. And that implementation in hardware was iterated on for many years now. And when we are talking about potential speed up that can be had with an ASIC, so like a physical circuit designed for this specific purpose, it is something like 3x at best, which is fairly small speed up comparing to some of the other algorithms, which can be sped up like 1,000 times or more. And that is basically the decision why we decided to go with AES. And in the future, we actually plan to build an ASIC if we stick with AES that will get most of the way to 3x, and we will just distribute that to community, and then everyone will basically have the same kind of performance. The reason why we want to have high performance is basically going back to why we have proof of time in the protocol. There is a special kind of attacks, long range attack on our protocol without proof of time, that basically says you can attack the network, meaning you can build the longest chain if you have more than half of the average space pledged to the network over the whatever duration of the protocol is running for is, rather than more than half right now. So imagine the network starts with basically 0, and then in a year it reaches, let's say, 20 petabytes or something. You only need an average of the space throughout the year, which is way less than 20 petabytes, to actually attack the network. So you can attack the network with something like half a petabyte, probably, depending on the curve of the space pledged increase. And if we introduce proof of time, then not only you will have to have more than half of the average space, you will also have to spend 1 year of physical time in the real world to get to the same height of the blockchain, which means that you basically can't, right? That is the basic idea, and why we want to have an ASIC and why we want to have the fastest implementation possible today is, if someone can evaluate proof of time faster than real time, significantly faster, like twice as fast, then they need, let's say, half a year to get to the same height. So basically, we want to have the fastest implementation we can find, practically, this means right now we will take like the fastest overclock CPU we can find, and we will run proof of time, and hopefully some community members will run proof of time on those as well, and that will be our baseline. But once we have those ASICs available, we will just increase the number of the parameters of the protocol, and we will make proof of time harder, and that will be a new baseline security for us. Hopefully that makes sense as a background, why we want to have it. The underlying primitive is AES 128. We basically have an input, and we have enough number of iterations that we want to run AES for, and then we basically iterate it in a loop. If you are familiar with AES, you know that there is a data and there is a key, and you encrypt the data with the key. In our case, in terms of parameters, we have a seed that is our data, and then at the beginning of everything, we hash it once, we get a key that way, and then using that key, we just evaluate AES once, then we take the output, treat it as input again, and we iterate that loop many times. Specifically, I believe something like 185 million times right now. That's what my CPU can do in 1 second. It will be higher for the mainnet with newer processors and higher frequencies. So that is the underlying primitive. And ideally, if we parameterize it correctly, after that number of iterations on the fastest processor we can find, we will have 1 second of time spent in real world. So in the previous version of the protocol, when we didn't have proof of time, we just took a clock, and basically every second it would tick, and we would try to solve a puzzle, our proof of replication, proof of archival storage puzzle. And in this case, our proof of time becomes a puzzle. So every time we do that 185 million iterations, that is a second. That is when we try to solve. And I have a small diagram here to show how it works. Basically, we have an arrow of time to the right. The genesis block is basically given for us. We don't really do anything special about it. And then on every certain number of iterations, we get a slot. And then on that slot, we will try to solve a puzzle. From proof of time output, that the last output after that many iterations, we will drive a randomness that farmers use to solve. Basically, farmer implementation is the same as it was before proof of time. Farmer doesn't know anything about it. It's just the way that the randomness derivation is done has changed. And every slot they will basically try to solve. And if they have a solution, what they will have to do, they will actually have to wait, in this case, 4 slots before they can produce a block. There is not a diagram where this is like shifted, but I think this way it's easier to understand. So basically, when we produce a block for slot 2, in this case 0, 1, 2, do you see my cursor, right? I hope. Can someone confirm? Okay, awesome. So here on slot 2, we have a block, and we would have to wait for slot 3, 4, 5, and 6. And when we produce a block, we will include proof from time slot 6 in the header of the block. So solution, we know solution beforehand, but we cannot physically produce a block because we don't know this. What this means is that we have essentially a prediction window, in a sense that every farmer, regardless of how quickly or how slowly, they can actually scan the disk for solutions or produce a proof that they have a solution. They essentially have 4 seconds to do that. And then after 4 seconds, they have this future proof, the way we call it, and that future proof is sufficient to start building the block. So block is built here, like in real world, like it's already in the future, but it corresponds to the slot here, and block the slot in the block is slot 2. And that basically repeats every time. Every now and then you will have a solution. And I can show you how it works in the code quickly. So in the sequence of Subspace, we have a slot worker, and then we also have a C proof of time, which is client components of proof of time. In here, we have a function that is called start slot worker. There is the same function in SC consensus slots in substrate that is based on time. In this case, it's based on proof of time. And essentially, we have a stream of slot information coming from proof of time. And what we will do, we will notify our worker our worker in the consensus. In here, we have slot worker. We will notify that there is a new proof. So this new proof, this is what happens like in real time. Like every second, we will just notify that there is a new proof. There is a new proof. Do if you want something about it. And there is a function here on proof, and we would basically do everything we need to do to derive information for the farmer. So we will take the global randomness, for instance, derived from that proof of time, and we will just notify the farmer, here's your challenge, go do the calculation or farming, whatever. We just don't, but we don't wait for the farmer to reply us with something. And then we will try to subtract the delay. This yellow is the delay in 4 slots in here of the future proof. And then if that is not, let me see, if that is like not underflowing number, we will notify the slot worker the same that we just told that there is a new proof. We will notify that there is a new slot for which you can actually solve. So essentially, when we have a slot 6 here, we will notify the worker that you can now produce a block for slot 4, for slot 2 if the difference is 4. And that way, we essentially have decoupling between when we farm and when we produce a block. So the production of the block is very similar to what it was before. We still have claim slot function that will try to compose the pre-digest and everything, and it will basically produce something that is either vote or block in the end. But we also have this addition on proof that we didn't have before proof of time. Okay. How do we actually get these slots? There are actually kind of 3 ways, but mostly 2. We have a new thing called proof of time source, and that is basically like a beacon of time slots or like proofs of time that can come from 3 places. Conceptually, there are 3 things that are happening in the protocol. There is a notion of a timekeeper. This is one of those like super fast processors that can evaluate AES the fastest in the world. And there will be a few of them. They will each try to produce these proofs every second as fast as they can. So that's one option. But obviously, not every farmer has the fastest processor, so they will not do that. That's like an optional feature. You need to specify dash timekeeper on the node when you started to actually do this. The other alternative is all of the timekeepers that have produced the proof, they will broadcast it to the network. And you can receive a gossip with the proof from the network, and you will re-gossip if it's valid to others. That's the other way how you can actually get it. So in practice, most farmers will get these slots with some small delay after they receive it from the network, not just produced locally. There is a third case, fallback. For instance, when you are thinking from deep history, you will actually ignore gossip. You will not run timekeeper either, so you will not have any proofs. But there is a third source, which is the source of truth, which is the notification that the block was imported. And since every block will have a pointer to the current proof and the future proof, and we verify all of this during block import, we know it's absolutely valid. So that is the third source. And actually, when we receive the proof here, that is actually different, or like different branch of proof of time chain. Essentially, it's like every proof is built on top of the previous proof, so it's like a chain. If it's like a different fork of proof of time, it will reorg everything. So basically, timekeeper will reset to the best slot known according to the block and everything like that. So this is the source of truth, and these are more or less like optimistic, a little bit, um, proofs. So there are three sources, but in the end, this source of proofs of time will just return you a stream that you can listen on and receive those, process those notifications. So that's conceptually how it works. What else? Let's go into the, there are two things. Let me switch to a different branch here. This is the newer iteration. So the way block production works in Substrate, the way block processing works in Substrate, you have kind of two steps. You have, when you receive a block, you will verify it, and that verification is supposed to be stateless, meaning that you will get a block in isolation, and you can ensure that the block makes sense in itself. You don't know if it belongs to the chain. You don't know if it extends the proof of time chain correctly, but you know that internally, like header corresponds to the solution, to proof of time included, like everything internally makes sense. So you can verify as much as possible there before you go to the actual block import, where you can verify that it actually extends the parent and the extension is correct. So you can do a lot of work in the verification, in parallel potentially for multiple blocks, and then block import will obviously be sequential because you need to import children after parents. So in verifier, there is a big block of logic related to proof of time, and there are actually two cases. So the fundamental case is when we take these two proofs, that's the only thing that is included, and we will basically try to ensure that, okay, assuming this proof is correct, we don't know for sure, but assuming this proof is correct and header contains correct information, we will try to ensure that this future proof is actually an extension of the proof. So we will try to prove that we have done 4 slots worth of iterations, accounting for entropy injection, which I'll talk about later. And that like all makes sense. That's what we can verify. We cannot verify that it extends something before that. We cannot verify anything about the future, past the future proof. But we can at least verify this. This is what we will verify. So here we will take information from our header. We will extract information about the number of iterations. We will take into account if parameters have changed, which includes potentially changing the number of iterations. As I mentioned, we'll increase it over time when new hardware becomes available that is faster. And we will also take into account the entropy. And then we will try to verify that the output is valid for the input parameters, that the future proof is valid. However, we also have kind of an optimistic kind of like happy kind of path here, because in Substrate there is a block, but there are also justifications. Justifications are usually used for finality. For instance, grandpa finality will be included later when everyone has voted and we have that information available. In here, we actually use justifications to include some extra information which will help us to verify proof of time faster. What do? We actually, like when we go from one slot to another, we have millions and millions of iterations. The way modern processors work, they receive instructions, but every instruction takes a certain amount of time to actually get to be executed. And then turns out you can actually pipeline several instructions, like put it in front of the processor beforehand, and then you can compensate for delay between different instructions. So let's say instruction takes 3 cycles, you can actually put 2 instructions one after another. So each instruction individually, if you like do one, wait for the result, do another, wait for result, it will be 6 cycles of the processor. But if you put 2 of them in the series right away, then it will be 4 cycles in total, because you will wait for 3 cycles once, and then you can do the next one right after that. So there is basically overlap between instructions, and turns out that when we do these number of iterations, we can put checkpoints in between. This is a chain block cipher that we do here, CBC mode of encoding. And if you have several checkpoints in the middle, we can actually do several things potentially. We can parallelize essentially encoding, or we can do decoding, or we can do encoding and decoding. And then with 8 checkpoints that we use in our protocol, we can actually have 16 essentially parallel streams of work. That is a lot of explanation. The gist of it is, if it takes a processor 1 second to go from one slot to another, like 1 second in the real world, by having 8 checkpoints and having 16 parallel operations, essentially, we can do the same. We can do verification 7 times faster on the same single core CPU, which is a big deal. We essentially spend a little bit more energy because CPU does do a little bit more work, but we spend way less time to do the verification, which is amazing. So the question is, where do we get those checkpoints? We don't include them in the header. The answer, we use justifications. We can put extra information in justifications. They will not be archived, but when block is produced, it will be sent alongside the block. And when you are syncing the last few, like 1,000 blocks that are not pruned yet, they will actually all be with justifications, so you can accelerate verification. So the kind of happy path here is that justifications are present. And if they are, then instead of verifying that we have done one slot of worth of iterations times number of slots between current slot and the future, we can actually do verification of individual checkpoints. In here, we just call verify checkpoints. And what it means is we can do this much faster. And then by the time we get here, this POT verifier will actually cache results of previous verifications. So it will know that these that we have a correct proof for these inputs, and then for the next iteration, it knows the other inputs, and that makes everything more efficient. What we actually include in justifications. So in justifications, we will include all of the proofs that were not seen on the chain yet. So when we are talking about the first block, for it, we will include, in this case, proof and checkpoints for slot 1, 2, 3, 4, 5, 6. Because none of them were seen on the chain so far. But for the next block, we will only include 7, 8, 9, 10, 11, because 6 was already seen. That is the basic logic. So not only we can verify that this current, like the proof corresponding to the slot of the block and the future slot correspond to each other, we can actually verify all of the proofs that were not seen yet. So when we get to the block import, the only thing we really need to check is that the input is correct and number of checkpoints is correct. This is just two comparisons. We don't need to do any AES. Everything was already pre-verified during the verification step, which is nice because verification can happen in parallel on multiple cores. And that means for the sync process, we can do it much faster. Now, if you have this mental model that every time there is a block that corresponds to a slot that corresponds to a proof, and there is a future proof, when you read these conditions in the code, it kind of makes more sense. So maybe I can walk you through that. So in here, we have this like basic check, because justification is not guaranteed to be present. The basic check is we go into the header of the block and we see if it claims that there is a change of parameters. If the change of parameters happened before the next slot, so basically it happened before slot 3 here, then we need to do something about it. Otherwise, we will essentially use parameters which were before the block, so like from the parent block. If it was changed on that next slot after the proof or earlier, then it means that there was potentially a change of number of iterations. So this slot right after the slot of the block itself should actually include new number of iterations. So that's what we're doing conditionally. And then we also check if the change of parameters happened exactly on that slot, next slot. So if it happened exactly on slot 3 here, then what we need to do, we need to inject entropy from the blockchain into proof of time. The proof of time, this one, so we need to have a new seed for this slot 3. Otherwise, we can just derive it directly without any entropy injection. And if we don't have any parameters change, again, we just take proof of time and derive seed without entropy injection. And then we need to verify that the extension from current slot to future is correct. So we take the next slot. This is the first slot for which we are trying to verify proof of time. So in our case, this is slot 3. And then we also look what the seed is. We have just computed what the seed is and number of slot iterations. How many slots we need to verify? This is the delay, block authoring delay. In our case, it's 4. So 1, 2, 3, 4 slots we want to verify. And then we also have the output. So this is the future proof of time that we should have gotten if everything was done correctly. And then we also give it the parameters change, because if it changes in the middle, let's say parameters were injected somewhere here, it needs to know and account for that when we do the iterations. So hopefully it makes sense, like logically. Any questions so far? Okay. So that is the verification. There is actually another portion of verification. So sometimes timekeepers can be a little bit offline. Timekeepers, they are running locally on a particular node, but it's not guaranteed that that same node, it's actually unlikely that the same node will actually also farm. So timekeepers are supposed to receive proofs, not proofs, blocks from the network. And not only they will know like what is the canonical chain, they will also have these injection parameters, for instance, entropy. If they don't receive a block, then they don't know what to inject, when to inject, and they will essentially start producing incorrect proofs. So the way entropy injection works, we have already talked about that. Essentially, we have one parameter which is called interval, entropy injection interval, and it is measured in blocks. So in this case, it is equal to 5. I have a legend at the top. So 1, 2, 3, 4, 5 blocks. And that 5 blocks interval is the interval. We have many of them. Then we have a second parameter, which is lookback depth, which is measured in intervals. And then we have a third parameter, which is injection delay, which is measured in slots. It's kind of confusing at first, blocks, intervals, slots all at the same time, but I hope it will make a little bit more sense in a second. So the way it works, every time we hit the end of an interval, so in this case, block number 6, well, 5 depending on how you count. If it's 0, then it's 5. And then you will try to look 2 intervals back. In this case, it doesn't make sense because there is not enough blocks yet. But for instance, here at block 15, we can look 2 intervals back, and there is a non-genesis block here. So we will look there, and we will try to derive an entropy from here. It doesn't really matter much how it's described in the spec, but basically we will take something from this block, in this case, block number 5, when we are in the block 15, and we will essentially store it. So every time, like we store it, okay, I expanded a little bit backwards. Every time we hit the end of the interval, we will store some information from this block in essentially a hash map. And then when we hit the time when the end of interval appears, but we also can look back, like in this case, we will look that thing that we have stored before. And then what we will say that this is the time slot of the block at which we have looked back, and we will add injection delay number of blocks, and we will try to inject this thing we stored here, this entropy, into here in the future. So we look back a number of intervals, take something from the block, essentially. In terms of runtime, we store it right away, but you can logically think that we just look back into it. And we inject it in the future, in this case, 15 slots in the future. So this slot is where we will take that into account. So this is where this condition, for instance, will be true. So that's how we essentially tie proof of time and blockchain together. So proof of time is the source of randomness for the blockchain. By the way, in the past, we have updated randomness in large intervals of, how much was it? 256 blocks or something like that. Now we update randomness every single slot. So unless timekeepers produce proofs and announce them to the network, farmers cannot do anything. I mean, technically they can run like a fallback timekeeper that runs slower, but at least at some speed. But otherwise, like unless they have proofs, they don't have a way to farm. So timekeepers are not incentivized, but they're like essential part of the network. So someone will have to run them. And then the history of the blockchain is based on the plots and the contents of the blocks and everything like that. So we need to take a piece of the blockchain itself back into the proof of time. So proof of time doesn't run on its own. And that's how we like anchor them back together. So every second we get something from proof of time into the blockchain, but then every now and then we take something from the blockchain and put it back into the proof of time. So unless you are following both, you will not end up with the correct kind of state of the world. Like if proof of time doesn't inject anything from the blockchain, it will stop corresponding to the blockchain and it will basically be like a useless fork of proof of time. So they must run kind of in parallel. Okay, let's go into the remaining verification. So one portion of remaining verification, why I explained how this works and why the timekeeper can actually fork. The reason for that is I actually caught that locally when I was setting unrealistic parameters, like a very low number of iterations and very small delay. I was like forking proof of time quite frequently. And it was the case that sometimes my blocks were not containing correct proofs, actually. But the way Substrate works, verification is only running for the blocks received from the network. It is not running for blocks that are produced locally. So in the slot worker, you can notice annoying block of code in, let me find it, in here, I think. Yeah, where we try to actually verify that proof of time actually makes sense. We only verify like a portion of that. We don't verify everything in here, but we just verify enough to ensure that the proof of time is extended correctly. Otherwise, we reject block creation. But if block is received from the network or locally, we still need to go through the block import pipeline. And in that case, we also have two branches. One is, as I mentioned, we just need to verify that the inputs are correct, the number of iterations, number of checkpoints is correct in the justification. But if you don't have justification, then we need to go through something a little bit more complicated. So this is if case when we have justifications. Else is when we don't have justifications. In here, we have two cases. In case this is the block number 1. So in this case, this is this guy at slot number 2. There was no previous block to get input from, so the input is actually Genesis. So in this case, number of iterations is whatever it is, but the seed is the Genesis seed. Otherwise, we will again look into the parameters of the parent block. We will check that there was some parameter change. If it was, we will take it into account. Otherwise, we will not. And then we will verify that based on the parent block, the proof of time of the parent block is extended to the proof of time of the current block. So we will verify that this blue slot was extended to this blue slot. We will not verify that this future slot is extended here, because sometimes it can actually be the case that there is not enough, like in here, for instance, the future slot will be the same as this slot, or this block can be produced even earlier, so the future slot of the parent block will be in the future comparing to the current slot of the ancestor. So that's why we verify iterations between two blue blocks, but that still should be efficient because, as I mentioned, we cache results of correct verification. So all of these essentially will be like almost free, and then we'll verify one more slot that this future is actually correctly extended. But logically, we extend parent proof of time slot to current proof of time slot and ensure that it is actually correct. So that's the remaining portion of proof of time verification that is happening when we import a block. There is a portion of logic in the runtime. Let me show you how the interface of basic proof of time looks like. Essentially, we take a seed and number of iterations to run, and number of iterations should be a multiple of checkpoints, otherwise it doesn't divide without remainder. And we derive key just by hashing it. There is a helper method here. And for verification, we take a seed number of iterations. We have checkpoints that will return us true or false. That's fairly simple. There is a portion of logic in the runtime. Let me show it to you quickly. So in here, yeah. So in here, what we do, we essentially maintain that map that I was talking about for entropy injection interval. So we have some number of iterations that is stored. Right now, there is no adjustment for it implemented, so we just like put it into the header in the consensus log items in digest, and then we will take this is like a hash map entropy. It's not one entropy, and then we calculate look back in blocks, and we will try to essentially find the number of the block at which we should take something. So in this case, when we are talking about block number 15 in here, the -2 intervals will be block number 5. So we know that we look into the hash map, we need to look into the entry corresponding to block number 5. And we compute a few other things. And then we also check if our current block that we are trying to produce here is actually the block that ends a particular interval. So the division, a result of remainder of division by the interval should be 0. If that is the case, we will just compute the entropy and store it in here, but we don't know when to inject it, so we will just store none. But then if we have a source number, so we actually can subtract two intervals and get something that is not genesis, then we will replace the target slot that we had there with the correct value. Wait. Yeah, it happens a little bit above. So we will look into the slot that we need to try to take to take, and if it doesn't contain the target slot yet, we will replace it. And then what happens is, so here we have identified that we need to inject the entropy. So after, like in this block and beyond, we know that we need to inject interval. So we will include information about that every single block until we hit this time slot. So this block will not have it, well, I, I I guess it might actually have, but the blocks beyond it will not have it. So that's why in here we will take the very first entry because they are stored chronologically, um, and we will check the target slot, and we will ensure that that slot is um, before the current slot of the block. If it is, then we will just remove it. Um, um, that is the basic logic of proof of time. I think I covered most of it. Let me think. Do you have, like, anyone have any questions? Anything that doesn't make sense?
I would like to know a little bit more about how does the timekeepers work? Because you mentioned that maybe some of the timekeepers nodes go offline. How many timekeepers does the network need in order to work properly with one and
The question from Nin is easier. No, they don't get any rewards, at least not right now. There is no punishment either, except they will be banned on the network. So it's not much point to do that. As to how does it work, um, let's go back to primitives. We have subspace proof of time, and in here we have a proof that we take a seed and iterations we get some checkpoints. The last checkpoint is, by the way, used to derive the next seed. And the way it works in a C proof of time, we have in sources timekeeper module. And what timekeeper does, they basically um, take information, what are the inputs for the next slot. So, like, what is the seed, what is the number of iterations for the next slot, and they will just call proof. They will try to produce next set of checkpoints. They will compose a message that will be sent as to sources to combine together, and they will extend what they think locally is the best um, tip of the proof of time, and that way they get the next input. They just run in loop forever. If it happens to be the case that there was a block imported and timekeeper was offline for some number of seconds, they haven't seen that the entropy should be injected, so they essentially forked. Will happen is this thing, try extend, will actually not be able to extend it correctly because what timekeeper thinks the input has actually changed. So the input they were working with wasn't correct, but they will still get the correct one in here as the output, so they can continue from like a new point. So they will essentially reorg onto the correct chain here. Does it answer the question?
yeah, thank you.
So basically, we have this like small piece of state in the SC proof of time, and there are two things you can do with this state. You can try to extend it, in which case you need to say what you think the previous state was, because if it doesn't match, then it will be ignored. Or if it's a block import, you know what the state should be, regardless of what it was before. Then you do the force update. So this update will potentially cause the reorg, but attempt to extend, which happens with both timekeeper and gossip, will only try to extend if it extends the correct chain. So that's how we separate kind of a little bit optimistic timekeeper, like it's not guaranteed that they are correct, from objective truth, which is the blockchain itself.
Maybe you could explain a little on where do we get like the initial seed and how would we prevent that people start running and producing blocks before
Oh yeah,
they can
that's
actually
interesting
do
one.
that?
Yeah, so there is basically a challenge that since proof of time runs in real world clock time, what if someone has started the chain before everyone else, right? So obviously, the first input that should be somehow accounted for is the genesis state of the blockchain. So the proof of time should be different for every different unique chain. That's obvious. But when we build the chain spec, we don't necessarily run the chain in the same second, but someone might have already started the chain. So we need to have some kind of way to prevent them from starting before everyone else. And the way we do that is with the genesis entropy. So you have seen in verifier there is a way for the very first block to take genesis entropy. I'll show you how we actually get it. So I think we can go back to here and we go to verifier and genesis seed. All right, just a parameter. Okay, so then we need to go into the service and we will see POD verifier. We will see that in addition to the genesis hash that we have when we start the chain, we will have a parameter called POT external entropy. That parameter in turn can actually come from two places as well. So we need to go to the node, and in the node, I think it's in lib. Yeah, there are basically hmm, maybe it's not in here. Probably it's in here. Yeah, basically we have this entropy, external entropy. It can be in chain spec. That will be the case when we build like a second release of the node or something like that. And that will be just embedded there. You don't need to worry about it. It will be called POT external entropy in the properties. But when we just initiate the chain for the very first time when we bootstrap it, we need to specify it through CLI parameters. So there will be a CLI parameter called POT external entropy. And if it is some, we will take it into account. That will be something like a hash of the Bitcoin block at a specific height. So when we launch the chain, we know the time when we want to launch the chain, we will predict what will be the block number of Bitcoin. And then everyone basically will be like a cold start, waiting to specify the hash of the Bitcoin block into the CLI arguments. And that's how we start the chain. All of the farmers can be already plotted with the Genesis segment. They will be ready to farm, but they will not get notifications, ghost notifications about slots because they don't know the correct proof of time. So everyone in the world will essentially be waiting for that block number on Bitcoin or something that we decide to use that has to be specified in CLI in the future in the chain spec before we can start the actual chain. Right now in the chain spec for the dev chain and for DevNet, especially for dev chain, the number of iterations is 100 million. And for the DevNet, it's 150 million. But for the actual like production chain, it's 183 to 170,000 iterations. This is what my processor can do. It's pretty fast, but probably not the fastest. So what this means is that if you have processor like mine or equally performant, you can actually produce blocks more than once a second locally, and it can actually play with this number to have slots issued faster or slower. The chain thinks that it should be 1 second, but what actually determines how much time it takes is this parameter. That's why if someone can run it faster, they can arrive at the correct solution sooner than everyone else, which is a problem. So if you develop locally, you can potentially change this. Or if it produces slots very like too often, you can put it like 200 million, 300 million. You can make it like slower. Okay, what else we have in this spec? This is kind of the idea how AES works. We have seed, we have checkpoints, then we do it again. Some algorithms. Farming. Yeah, one thing that's we're still discussing it a little bit. When we are thinking blockchain from Genesis, we will have hundreds of thousands of blocks, and every block on average will have 6 slots worth of proof of time verification, which, as you can imagine, is quite a while, even if you parallelize it on a few cores. So what we are doing about that is we have a special kind of algorithm for the major sync situation, which is deeper blocks. And what we'll do, we will only verify some proofs of time probabilistically. So depending on how deep the block is, we will have certain probability that the block is verified, and then we will just like generate a random number and see if it is within range, and if so, then we need to verify proof of time for this block. This is the kind of the basic idea here. That's something that was worth mentioning. This needs to be deleted now. And yeah, I think that's it. There is a new host function that's for those who care even more about implementation. Where is it? I think it's in the service. I can show you the API. So basically, there is one small challenge. We have a thing called vote in the protocol, which is an extrinsic you can produce if you don't have high enough quality to produce a block, which you should receive reward for. The question is, how do we verify it? What can happen is we have, let's say here we have a block 2, and on top of block 2, someone will produce block 3, obviously. But someone can also produce a vote, let's say here. What it means is that this vote is completely out of range of what could have been on chain up until this point. Moreover, it actually points to something in the future. So there is like no way this no way before this block is produced we can verify this transaction, but we need to verify the transaction when we actually receive it. We need to make a decision if it's valid or not before we re-gossip it. And the way we do it, we actually need some additional APIs into the host to do so. And that is a new host function. Let me show it to you. Yeah, there is a proof of time extension that you can call. I'm not sure where the function is. Oh, I guess it's in here. Is proof of time valid? So basically, you can say, how does it work? As of the block, this whether this proof of time would have been corrected for this time slot or not. And the way it works is with the assumption that both blocks and votes will include future proof. So the vote will look kind of like this, but it will have like a almost header and no body. That's how votes look in Subspace. So it should have the future proof just like the current proof. And if we receive, let's say here, our vote, it means that it should have been produced after the author received this future proof. So the assumption is that by the time we actually get this vote, we also should have seen at least this time slot. Maybe not this one. Maybe they are like super fast, but we should have seen at least this one. It has been like 4 seconds already. So what we will do, we will call into the host and we will say, okay, I know that there was a parent block number 2. This is its hash. The hash is necessary so we can see the injection parameters if they were to take effect. And we will say the slot for which we want to verify the proof, and we will give it the proof. And we will say quick verification true, because we should have seen and verified it. And then if it verifies correctly, meaning that we have already cached the correct output, then it's a cheap operation. We just say cool. Otherwise, we reject this transaction and we will throw it away. However, we also have a future proof that we need to do something about it. We will take care of the future proof only when we actually get to produce a block. So when we produce a block 3, we will actually go through all of the extrinsics again, even if they were verified when entering transaction pool. We will verify all of them again, and we will not only verify that this proof is correct, we will also verify that the future proof is correct. Why? Because when we receive this block, well, like when we get to produce this block, we should have seen even further into the future. So all of this proof should be known, and again, this should be a cheap operation to verify. However, there is a case when this block is not just announced. This block might have been just downloaded from DSN because it's a deep history block. So when we actually do the block processing, we will set this parameter quick verification to false, because during deep verification, deep sync, we will not have seen these proofs, none of them, and we need to do like full, potentially somewhat expensive verification. But that's the only way to deterministically and properly verify that this proof is correct or not correct. Yeah, that was one thing that we cannot possibly do in the runtime, at least for transactions that were gossip to us. So we had to introduce a new host function, unfortunately. The second one is the verification of solution, because there is a proof of space there, and it's too expensive to do in the WASM environment right now. The math is too expensive. So yeah, I think that is about all I have. Any other questions? Emil, maybe something that other developers outside of Subspace team might be interested in?
Yeah, I can't think of anything right now. It's a bit difficult for me. So it's like what you said it all makes sense, but I can't think of any specific question right now.
Okay, fair enough. Yeah, it takes a while to process, but I think with the right visualization and some background, it's certainly much easier than having no background at all. Because me and Daria, we've read this POT spec top to bottom a few times. For others, it might be just a completely new information, but it is helpful, I think, to understand like what time is and how we measure it. Yeah. All right. If anyone has any other questions in the future, feel free to join our engineering channel in Slack or drop a topic on the forum, and we'll try to answer it.
Yeah, I wanted to maybe add something about the incentives for timekeepers. So like right now, they're not incentivized as being asked, and they're not punished either. They do have an implicit incentive. That's why we call them like altruistic timekeepers, because if nobody run a timekeeper, then nobody can produce a block, nobody can produce transactions and no operators, and nobody can get rewards. So somebody has to run it. So that is one implicit incentive. For explicit incentives, we did consider adding them at some point, and we might. However, right now, they do stay altruistic, and it's also like the way that they work, for instance, like in Chia. So the assumption that somebody has to run it for sure is enough for them to run.
Yeah, the assumption is that there is at least one timekeeper running at any point in time. So hopefully not just Subspace, but even if Subspace is running them, we will run several. So when we upgrade one, we still have others. And there is a challenge with incentivization because we need to include some kind of information in the proof or like set of checkpoints that this was produced by a particular timekeeper. And usually the way we do it is like a signature, but then everyone can receive that, remove the signature and put their own signature on top of it, and also every message then becomes distinct because signature is different. And we would really like for messages to be canonical because then every message we are gossiping is the same, so the gossip mechanism actually works. We will gossip message once and not multiple times. So there are like several challenges with incentivization, but as long as the chain is useful to someone, there should be someone producing those proofs. Okay, thanks everyone for your attention. I think that will be it for today. And yeah, as mentioned, if you have any questions, feel free to reach out. We'll see you next time.